Okay, thank you for the nice introduction. I also want to thank the organizers for the invitation. Today I'm going to talk about code-based cryptography, where codes have the rank metric. So normally when people talk about code-based cryptography, the codes have Hamming weight. So today's talk is a little bit different from what you used to hear from other code-based cryptography. So I'm going to talk about main problems in post-quantum cryptography and code-based cryptography system, and also then what is the rank metric codes, and what's the corresponding code crypto system based on rank metric codes. And then important thing is to construct low rank paracheck codes. So I'm going to explain it a little bit more. As you know, the Peter Shor, who was actually originally coding theorist, okay, gave an quantum algorithm to solve these two famous problems. Therefore, this RSA and Diffie-Hellman key exchange, or the ECC, will be broken under quantum algorithm. So that's why people try to build find a new crypto system avoiding these mathematically difficult problems. And well, from yesterday until now, we learned the shortest vector problem and the closest vector problems. And these problems do not yet have a quantum algorithm, so it will be considered safe so far, but who knows? In the future, it can be broken under another quantum algorithm. So it's not still the confident algorithm until we completely know that there is no quantum algorithm for this system. So anyway, people say that quantum computer will be available 10 to 20 years. So we have to prepare for really post-quantum cryptography. And therefore, the NIST, since last year, plan to suggest a proposal focusing on these three topics. I think those three topics are very important. But today I'm going to focus on key encryption. So there are at least four quantum resistant algorithms, but I'm going to focus on encryption part. So lattice-based cryptography or code-based cryptography are relevant for encryption rather than maybe there are some signature schemes based on lattice and codes, but we focus on only encryption part here and here. As a coding theory background, I try to understand lattice-based cryptography in terms of usual lattices. Because the long time ago, Kone and Sloan wrote a book on sphere packing and lattice. So in that book, there is a very close connection between code and lattice. So we can construct very good lattices from self-dual codes. So that's by construction A, it's called construction A, or sometimes construction D, depending on the ground field. So there's close connection. Also, some people try to classify lattices, some very good lattices called the unimodular lattices, using coding theory techniques. So there is a close connection between code and lattices. So I look at the problem, the very important problem in lattice-based cryptography. Surprisingly, this closed vector problem is very similar to the syndrome decoding problem in coding theory. So there is a really almost same concept between these two problems. So I was surprised. So I tried to see more connections between the lattice-based cryptography and code-based cryptography. Another one is that in the Euclidean, in the lattice case, we have a bunch of vectors and in Rn, so we try to find their distance. That distance is called the Euclidean distance, correct? So, but in coding theory, where we use only finite fields and their vector space, so we have the so-called Hamming metric. Okay, this is count number of coordinates where the elements in each coordinate are different. So the this is more or less a classical one since Hamming introduced in 1946 or 7. But today I want to introduce rank metric concept in the study of coding theory. Even coding people, actually one of our the experts in Korea, Professor Jong No, maybe didn't hear about rank metric code. Did you hear about rank metric code? Yeah, he is a really expert. He already knows rank metric code because the rank metric codes are also used in network coding and some steganography and as well. So this concept introduced maybe 20 years ago by Gavidlin before. So, but these days the Philip Gabroit introduced this rank metric codes in the form of low density parity check codes, so which is an analog of low density parity check code from coding theory. So since then, I became so interested in this rank metric low density parity check codes. So that's why I was interested in this code-based cryptography, because I have worked on the classical LDPC code before, so I know that area and I know some of the lattice parts. So then let's combine these concepts together to understand the rank metric based code crypto system well. So this is what I want to explain today. Here's the key size about these various crypto systems. Well, these are well known, so they have very relatively small key size, public key size, and private key size for these well-known lattice-based crypto system. However, this code-based crypto system, introduced first by Megalis long time ago, will have this level of security using this 8 million bits. This is too big. We need 8 million bits to be safer for public key size. This is because in the code-based crypto system, the public key size is the matrix, the big matrix. So we need a large size n by n matrix. So it gives this many sides. And however, if we use a very well-chosen generator matrix or paracheck matrix called the double circulant one, then you don't need to store all the elements in the matrix. You only need to measure only the first row of the matrix. So the key size will be very small, but it has also nice security level as well. I'm going to explain this one a little bit more later. So here is the relation between codes and lattices. Since most of people here understand the lattice better, you look at the left side and try to convert this one to this code area. So in the lattice, we start from Rn. R is a real number, and that is converted to finite field with Q elements. Okay, and the lattice can be converted as a linear code, which by definition is a subspace of GFQTDN. Okay, this is a definition of linear code. So linear code is very simple to define, but we have a nonlinear code, which is just a subset of GFQN. So it's a very easy concept. And also we have a non-lattice concept as well. So the sphere packing requires either lattice packing or non-lattice packing, blah, blah. So this corresponds to this concept. And as I said before, we use Euclidean distance, okay, in the study of lattices. And however, in code we use mostly Hamming distance or maybe 1994, we used the Lee distance. That's another distance. Lee is not a Korean, maybe someone else. So and then we have other homogeneous weight or distance from very mathematically defined code, but we do not worry about that now. Only rank distance or rank metric will be used for code-based cryptography. And given a lattice, we try to count the norms, the lengths from the origin to the vector in the, the lattice vector. So we count that. That's called the Serra series. So the minimum, the shortest vector problem basically is to find the first non-zero or the smallest non-zero norm in this zeta series. Okay. So this one and this. So if you solve this one, then you solve the first non-zero coefficients of this zeta series. And that corresponds to weight enumerator of the code. And this is 8-dimensional lattice. This is 24-dimensional densest lattice in the world, including lattice and non-lattice. It's a very recently it was proved that rich lattice in 24 dimension is the densest lattice, densest packing in the world. Before it was densest lattice packing, but now it includes non-lattice as well. And these two topics correspond to Hamming code of length 8, dimension 4. And this is the 24, 12, 8 Golay code, binary Golay code. So this is a close connection. Corresponding groups are here. Maybe you are interested in this one. The shortest vector problem basically corresponds to minimum distance problem of a code, which is hard to find in general. And closest vector problem corresponds to, as I said, syndrome decoding problem. But another name for this one is the nearest neighbor decoding problem. Okay, so about the same name. Closest vector, nearest neighbor is the same name. And in coding theory, these two problems turn out to be NP-complete. And this is hard enough. So the same concepts are used to study code-based and lattice-based cryptography. And from NTRU, we have the concept of ideal lattice, but that corresponds to cyclic codes. And in LWE, public key, yes? So I mean, this is the lattice, which is cyclic. So, oh, really? So I'm sorry. So then this, I mean, this is the ideal lattice. I thought this concept comes from NTRU. Yeah. So this one. Okay. So then I correct this one. So I thought the lattice concept, which is cyclic, corresponds to cyclic code. This is what I want to say. Okay. And this LW public key has two keys, public keys A and B. But this size, this part, corresponds to the encryption of the message using this public key. G prime is public key plus error vector. So this is the encryption, but the public key here for LWE, announce this A and B. So this part is exactly the same as this part. Okay. Although the decryption here and the encryption and decryption are different, but this part is the key, the most important part, and that is about the same as this form. So there's a close connection. And yesterday, Professor Chun talked about some very sparse metrics. And from coding theory point of view, that can be understood as low-density pattern check code. Unfortunately, in coding theory point of view, this LDPC code are used as an input of MAC-Alice crypto system, but this was broken because this LDPC code are good from communication point of view because of its fast decoding algorithm. However, in many cases, it has a very low weight code word. So it can be that information helps to break the system. But here I do not know what's the effect to leak the information of the sparse matrix to weaken the system. So maybe even though in this area the sparseness does not have a good effect, but I do not know for this area. So as I said, McEllis crypto system was introduced by McEllis 1978. At the time, he used the GOPA code. But very strange thing is that these days we do not use GOPA codes, but only in the crypto system we use GOPA codes. That's very strange. And there are other fancy codes, classical algebraic codes, algebraic geometry codes. There are many codes, but these codes have some disadvantages so far, so they are not used for crypto system. So only GOPA codes with these parameters. This is the parameter. So the original one has length 1024 and k equal 524 and t equal this. So this is the parameter. You can easily plug in here. And but at that time, it has a large key size, so it was just like a theoretical crypto system. But if you want to increase the security level, then you have to just choose a larger length, larger k, blah blah. So we can still have the various security levels depending on these parameters. So still it's unbroken. But as I said, the main problem is the key size of the public key, because we have to announce the very big generator matrix. That's the headache for crypto system. So here's the question. We try to build codes based on McEllis crypto system having these properties. The key size won't be about 1,000 bits, and it's secure under decoding and structural attacks. Okay, the matrix shouldn't after some scrambling shouldn't be distinguishable from some structured one. So we have two kinds of attacks. One is a structured one or a decoding one. And also, well, this part is normally accepted. In other words, if we use code-based crypto system, then it has fast encryption, and if you choose a good code having good decoding algorithm, then it has a fast decryption algorithm as well. So the encryption part is easy, but to have a fast decryption, you have to choose a very well good family of codes having good decoding algorithm. So that is the problem, one of the main problems. So not many codes can be used. So here is the list of the codes having not relatively good decoding algorithms, but as I wrote here, those have been insecure under certain attacks. So even LDPC codes have low weight code words in their dual. So it leaks key information. So it was broken, and Reed-Solomon codes are very widely used in compact disk, but it also reveals some information of the structure. So even Lido-Miller code or elliptic codes or algebraic geometry codes are not secure so far. If you modify something, then it can be secure. So, but currently it's not secure. And Lido-Miller codes also, based on some other algorithm, it's not secure. So highly structured codes are not good, and this is not highly structured. Those are not good. So the choice is then either you give up using codes, or you find another new class of codes. So that's why the new metric, I mean, instead of Hamming metric, if we use Hamming metric, only GOPA codes survive. So then it's time to change the metric. Okay. So here is the rank metric. Actually, it was introduced by who are looking a long time ago, but this code was used in crypto system first by Gabidulin and et al. In 1991, and then so it's called the GPT crypto system at the time, and people tried to attack it, and at certain parameters it was attacked. So the Gabidulins tried to modify their system, and so they are still trying to modify their system. And in this system, they use I didn't write down. They use Gopak, actually the Gabidulin code, which corresponds to classical Reed-Miller code, Reed-Solomon codes. Okay, so they are still trying to use the Gabidulin codes in this system and changing the encryption a little bit. So they are still working on it. And Gaboroid revisited his idea, replacing the Gabidulin codes by the low-rank paracheck codes. So simply LRPC codes. Okay, and because I don't know why he really think about LRPC code. Maybe one of his co-authors, Jelmer is familiar with LDPC code. So maybe Jelmer suggested to imitate the concept of LDPC code in the low-rank paracheck code. So maybe I think this is my guess. So they come up with this new class of low-rank codes. So and then they check that it has very good performance. I mean, the key size is small, and it has high security level. So they publish many papers these days. So today I want to explain some of their result. and so basically, as I said here, they come up with this LRPC code concept because this class has a very fast decoding algorithm as well. So now it's relevant to use as an input of McEllis crypto system. So the concept of rank metric comes from the who are looking, and then Deljat, who is a famous combinatorialist. Here he used any m by n. Here is a square matrix. This is a m by n non-square matrix. And then Gabidulin introduced the rank metric concept in a vector. So if you first study this rank metric, it's a little confusing because we have a vector, just one vector, but we convert it as a matrix. So that's not really standard before. So here's the definition. Let the vector be a basis. So it has m basis vectors over GFQ. And we have a map from GFQ to the M to GFQ. So this given X, which is in here, you can represent X as a linear combination of these things. So you have a M coordinate. So this represents each coordinate. So given a vector in GFQ M to the N, so each VI is in here, GFQM, and represent each VI using beta here. So replace this VI as a column vector whose size is m by 1. Okay, so it's just represent each VI as a column vector based on this basis. So you keep writing it, then you have a matrix corresponding to this vector. So it is called VVA. So the rank weight of this one vector is the rank of the matrix VVA. That's the definition, formal definition. Okay. And if you change the basis, still the rank weight doesn't change. This is basically just a span of these columns, and so the dimension doesn't change. It does not depend on the basis. So the rank will be the same. So we simply denote the rank of V by rank V. So given two vectors in here, you can find the distance by rank V minus W. So this distance is called the rank metric. Okay, it gives a metric. So it's a little bit confusing. So here is an example. Because of this definition, it's enough to understand what is just the rank of V, some vector. Okay, rank of V instead of distance between two vectors, since distance between two vectors is exactly the same thing. So what is the rank of a certain vector explicitly? Here is GF2 to the 4 as a 4 tuple of over GF2. So there are 16 elements, and we represent each element as a 4 tuple, binary 4 tuple. So given a vector here in GF 16 to the 8, maybe 10, yeah, then each element, say alpha to the 8th, is replaced by 1, 0, 1, 0, and keep doing this. Yeah. And the question is, what is the rank of this vector? Even though Hamming weight is 7, because there are 7 non-zero elements, it's big. However, the rank weight is just 2, because you replace this by a column vector of length 4, and similarly. And then you have 1, 2, basically 3 different non-zero vectors. However, the sum of these two will give you this vector as well. So only 2 columns are linearly independent. Only 2 columns are linearly independent amongst 10 columns. In other words, these 2 are linearly independent over binary field. And this alpha 9 is actually the sum of these 2. So the rank metric basically is to look at the all coordinates here, all coordinates, and try to eliminate any dependent coordinate, and what's the maximum number of linearly independent coordinates. That's the weight. That's the rank weight. Okay. So by intuition, it is much harder to find the rank weight than Hamming weight. In the Hamming weight, you just count whether it's 0 or not. There are 7. There are 7 non-zeros, so Hamming weight is easy to find. But for the rank weight, you have to look at all their linear combination, so it takes more time. Okay. So the rank code, by definition, is simply a subspace of dimension k in this large extension field, okay, with n. But the rank, it has rank metric, and inner product is the usual inner product, the component-wise multiplication. So, and minimum rank distance is the minimum rank of any non-zero vectors in the code, okay. So if you drop this rank, this is the definition of the code and minimum distance. Okay, and this concept is not used in classical coding theory. If you have a vector whose rank is r, and then you look at all these coordinates and span it over GFQ, and so the space spanned by V1 through Vn is called the support of V. So this concept is different from usual supporting of a vector in under Hamming weight. And if you have a rank metric code, and then it's easy to construct the codes with 80 bits security level, but the key size is just a few thousand bits. However, if you use Hamming weight, then the key size should be 100,000. So that's the advantage having rank metric. So among rank metric codes, we are interested in low rank paracheck codes. In other words, when we define a code, we can define a code as using a matrix H. So the code word will be a vector such that Hx equals 0. Okay, so this is another way to represent a code using so-called paracheck matrix. For RLPC code, we give a condition saying that the entries here, Hij, will form a vector space. So you span those elements and form a vector space, and the dimension over GFQ is at most D. So D is a number we define in the beginning, and we want this D is small. Yeah, it's kind of small, like 3 or 4 or 5, okay, not big. So it is called row rank because the rank is row. And the space spanned by those HIs will have then rank D. So you pick only D elements from there. So this is denoted by F. Okay, so this is the concept. And there are two famous families of RLPC code, and one is quasi-cyclic RLPC code. It has a paracheck matrix, which is a quasi-cycling matrix. Okay, quasi-cycling means it's a generalization of a circulant matrix. Circulant means you have one row, then you shift one by one for each row. For quasi-cyclic, you shift 2 times for 2 quasi-cyclic, 2 times. So and then it's closed under addition. So keep doing this. But this double circulant means you shift first element one more. So the first element will be put in the third element, and the second element will be put on the fourth element. And so that type is called double circulant. Okay. And double circulant matrix can be reformulated into the sum of 2 circulant matrices. One left side circulant and right side circulant. We can convert that one in this form. Okay, so it's a concatenation of 2 circulant matrices. Oh, okay. And in the study of a rank metric-based crypto system, we assume that this rank syndrome decoding problem is very hard. And here is the problem. Given a matrix H, which size is n minus k by n over this large field, k is of course less than or equal to n, and choose arbitrary s in here, q to the mk. So this h is n minus k by n, and x this exercise should be n. Yeah, I think this should be S is here. Sorry, S is here. So I think this should be, hold on, H. I think this should be n minus k. Yeah, because this is the matrix product. So you try to find x, which size is n by 1, such that hx equals given s. Okay, so this is the syndrome. It's called syndrome. And also we have another restriction. The rank of x is equal to r. So this is the syndrome decoding problem based on rank metric. So this is rank matrix. But this is very similar to usual syndrome decoding problem for Hamming metric, where we replace rank by weight. Weight x equals r. That's the only difference. The rest is exactly the same thing. And it turns out that that problem is NP-hard by this Meg Ellis and Burlecombe and Tilburg, very famous coding people long time ago. But because in the previous example, I said that finding the weight, rank weight of a vector is a little bit, looks harder than finding the Hamming weight of the given vector because of the nature. So since this problem is hard, and it looks like this problem is harder or same hardness, but it's still open problem. Okay, even though there are some result, but people still try to completely answer this question. So this is just idea why the attacking codes based on Hamming metric is easier, in some sense, easier than attacking codes based on rank metric, because normally we have to count the number of words, not necessarily code words, number of vectors of length n and support size t. So there are n choose t. We have to consider n choose t elements. But in Hamming, rank metric code case, you have to find t-dimensional subspaces in n-dimensional space. So that number is Gaussian binomials nt. Okay, so this is much bigger than this. So that's why attacking codes based on rank metric is harder. But if you use LRPC code, then it turns out that it has a very fast decoding algorithm. So the complexity is like this, depending on D and R. So when D and R small, then the complexity is small as well. But one the disadvantage for this algorithm is this failure probability. In other words, the decoding cannot decode an error with this many the probability. But for the actual parameters like this is double circulant case. Double circulant means you have circulant things together, but only repeat the two. You have one circulant A and another circulant normally B, but we have AA. So to describe double circulant LRPC code, you need to specify the first row of matrix A, because you are going to repeat it. So if you choose these parameters, then the failure probability, you just plug in n equals 82, k equals 41, and 1 r times d, then it turns out that it is 22. So the probability that this decoding algorithm cannot decode the error is 1 over 2 to the q equals to 22, which is very small. So even though there is some failure error, but still it's reasonable. And the public size, how do you get the public size? This is paracheck matrix coming from double circulant, so it's a half. You use only half of this, so 41, and 41 times, and this is the m, so that is 41 times 41. This is n minus k, so the size, matrix size is 41 times 41, and which is this, okay? And similarly, half of this times 53 with this. And for this one, you multiply the half of this times m, but this is over gf2 to the 4, so multiply 4, then you get this. So public key size increase depending on these numbers. But the error probability here is getting smaller and smaller, and this is security level. So we have a reasonable public size if we use this DC LRPC code. But the problem is that they suggested a few years ago, and not many people attacked their crypto system. As I said, there will be decoding attack or structural attack. So these are not done yet. Okay. So this is the algorithm, but this is the same thing. Basically, Megali's crypto system, the encryption is always x times g prime, and g prime is in their case original secure matrix times the invertible matrix on the left side, but normally we have extra thing on the right side. They skip that one. So we can add more information. We can modify the encryption by adding more columns and scrambling those columns together. So this is the classical one, but they didn't use it in the LRPC code case. So it's possible to use this one. So LDPC code is a classical code, but in the beginning of the lecture, I give a brief idea about this code. Basically, the paracheck matrix has only few ones, and the rest are 0. Okay, then it has a very fast decoding algorithm. And the problem is how do you construct the LRPC code from LDPC code. So here is some idea. I use Euclidean geometry or projective geometry as an object. And in the Euclidean geometry, we have this instance matrix from points and lines. So it's a geometry, finite geometry. So you have a point concept and line concept. Whenever a point belongs to a line, then you put on 1. So the rows are indexed by points and the columns are indexed by lines. So you can easily put 0 and 1. Just like in graph theory, we have instance matrix from point and edges, okay, the vertex and edges, same thing. Then you have a really 0, 1 sparse matrix. So that is H, okay. And then we modify a little bit. So for those non-zero ones, you replace some large finite field elements and carefully replace them. Then and then just shift the first row n minus k minus 1 times. Then we get a cyclic LRPC code as well. Okay, so you combine these two things. Concatenate these two matrices, then it will be really double circulant LRPC codes, which were used in the Gabrovitz crypto system. So this is they didn't actually give us some family of LRPC codes, DC LRPC codes. So we explicitly give them such codes. I think So as a conclusion, here is my personal point of view. So code-based crypto system were used by coding people, studied by coding people and some cryptographers. And this studied by the number theorists mostly, and LW is also another crypto system. But they have some good things and bad things. So if we want to build a very good crypto system, maybe we combine all good things together, and so maybe this one will be a very good crypto system. Yeah. So, So basically, maybe some hybrid crypto system based on lattice and codes will be a very possible crypto system in the future. Okay. Thank you for your attention.
So there is a question from online. Let me read the question. What happens if someone uses low Hamming weight, it means sparse, with same rank in LRPC code?
Okay, so we don't worry about low Hamming weight because we use totally different decoding algorithms. So I think even though the Hamming weight is small, but and also the LRPC has in terms of LRPC code, the rank is low. I think that that is also reasonably good candidate to this crypto system. So it's not bad, I think.
Any other question? Okay, so I just have a quick question. So you were a little bit worried about structure attacks. So what other things you really worry about? Like, can you be more specific on that?
Actually, this is an open problem in the study of this LRPC code case. So there are actually two problems. One is the decoding attack. So they suggest their own decoding algorithm. So is there any the problem? I mean, some weakness in their decoding problem. So in some cases, if you use cyclic code, then cyclic code has its own decoding algorithm, but that decoding algorithm reveals some information to the attackers. So we should not use cyclic codes for that reason. So I haven't seen on decoding attack for this crypto system, this LRPC crypto system.
Any other question? So if not, then let's thank the speaker.